having to drink our beverages through a straw from a bag. Makes you feel like you're a big insect sucking the juices from another insect. I wanted to see if I could figure out a way to have an open container cup in a weightless environment which would allow you to drink your tea and your coffee in a manner that's commensurate with how people drink their beverages on Earth. Taking some of my surface chemistry that I learned in college, I devised a cup with a special shape. The cross-section looks kind of like an airplane wing, where it has a cusp, and the cusp will allow channel flow, so the liquid from the bottom of the cup will float up and just park itself right next to the rim, and then you can drink it. And it allows a crew to share a communal beverage. You could share tea. Maybe you just come in from doing a spacewalk or something and you want to celebrate a little bit. If you have a real cup, an open container, it's so ingrained in human beings, it's so ingrained in culture, it adds back the dimension of what it's like to be a human being in a civilized way.
Okay, flames and fluids are acting a little differently. But that's not all. Take a look at how microgravity affects colloids, magnetic fluids, and smart materials.
If you have a smartphone, take it out and run your fingers along the glass surface. It's cool to the touch, incredibly thin and strong, and almost impervious to scratching. You're now in contact with a smart material. Smart materials don't occur naturally. Instead, they're designed by engineers working at the molecular level to produce substances made to order for futuristic applications. The Corning Gorilla Glass that overlays the displays of many smartphones is a great example. It gets its toughness in part from fat potassium ions stuffed into the empty spaces between old-fashioned glass molecules. When the molten glass cools during manufacturing, dense packed molecules solidify into a transparent armor that gives Gorilla Glass its extraordinary properties. Around the world, designers are working on other smart materials, such as alloys that can change shape on demand, plastics that heal themselves when ruptured, and fluids that obey magnetic commands to flow or stiffen under computer control. One of the greatest challenges in creating a smart material is arranging the molecules. They're so small. We want to create a new class of materials beyond smart. We need genius materials, materials that arrange themselves. The research to accomplish this is already underway on the International Space Station. Dr. First is the principal investigator of an experiment called In Space 3. In the microgravity of Earth orbit, vials of fluid mixed with very small colloidal particles, about a millionth of a meter in diameter, are exposed to magnetic fields. Magnetism can be switched on and off again very rapidly. This jostles the particles, causing them to bump together and self-assemble into microscopic structures. These structures can be very difficult to predict, even using cutting-edge models running on supercomputers. Astronauts enjoy watching this process in action through microscopes. Because the samples are backlit by a green lamp, they sometimes call it the green blob experiment. First recently won an award from the American Astronautical Society for his work on In Space 3. Just by toggling a magnetic field, we're learning how to take many kinds of microscopic building blocks and get them to spontaneously form interesting structures. Recently, observers have seen the colloidal particles forming long fibrous chains. First speculates that these could lead to materials that conduct heat or electricity in only one direction. The experiment has also yielded crystalline structures that the team is just beginning to investigate. The fluids underlying these tests are themselves very smart. They're called magnetorheological, or MR fluids, because they harden or change shape when they feel a magnetic field. If you own a sports or luxury car, you might have MR fluids in your shock absorbers. The stiffness of magnetic shocks can be electronically adjusted thousands of times per second, providing a remarkably smooth ride. Similar but more powerful devices have been installed at Japan's National Museum of Emerging Science and China's Dongting Lake Bridge. They're there to counteract vibrations caused by earthquakes and gusts of wind. Some researchers have speculated that MR fluids might one day flow through the actuators and hydraulic dampers of robots, moving artificial joints and limbs in lifelike fashion. Scientists and researchers are using these fluids as a laboratory for studying self-assembly. MR fluids are, by definition, responsive to the magnetic nudging that sets self-assembly in motion. Furthermore, in space, the particles don't sediment out due to gravity. We can study the full 3D evolution of the material. Varying the shape of the colloidal particles, the cadence of magnetic toggling, the temperature of the fluid, and other factors will allow researchers and astronauts to further explore the frontiers of self-assembly. Touch the surface of your smartphone again. That's just the beginning.
As you can see, our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. This work off the Earth will lead to a better understanding of the fundamentals of combustion, surface